so let's take a look. Our claim is actually, yep. So the claim is that 17% are, is this a mean or proportion?
Proportion.
How do you know it's a proportion? There's a percent, yeah, 70%. And also there's no mean or standard deviation on here. So my claim will be that the proportion is, right, ours is another word for is, 17%. All right, so step 1, H naught is always
P
equals. So P is equal to 17%. Great. Is that my claim? Yes, that is my claim. My claim is P is equal to 17%. So that's my claim. So what word am I going to use? Reject. Is everyone on board with that? Is that making sense to folks?
Yeah.
Okay. So here, my claim is that the proportion is 70%. My claim is that P is equal to 17%. That's H naught. Is that everyone kind of following that? So my claim is H naught, because H naught's always equals. So here, if I reject H naught, my claim is H naught. So if I reject H naught, what does that do to my claim? If I reject H naught, I reject my claim, because my claim is H naught. So rejecting H naught rejects my claim. So that's why I'm going to use the word reject in the summary. Okay, so here's the second thing. Since my claim is H naught, how would I reject my claim? My claim says I am 17%. How would I disprove that? What's one way I could disprove that? If I got something that was
P is not equal to.
Yeah, something that was a lot smaller than it, or if I got something that was bigger than it. So smaller than or bigger than, that means not equal to. So H1 would be not equal to, because that's how I disprove H naught is if P was not equal to 17%. Everyone feeling all right with that? Okay. Okay, so then we need to go to step 2. What's my alpha?
0.10.
0.10. And step 3. What kind of test is this going to be?
One problem Z test.
Yes, it's a proportion. So one proportion, one prop Z test, and I'm going to input my P naught, which is from my claim, and then I need to put in my X and my N, and then my H1, I believe.
Yes.
So from the claim was 17%, 0.17, remember you have to convert it to a decimal, because there's no percentage symbol. And then from my claim I had, yep, 42 people out of 200. So 42 is my X out of 200 people, and my H1 is not equal to. Everyone feeling all right with that part? Okay, so if you did that, what did you get for your Z-score?
1.51.
1.51? And your p-value was?
1321.
1321. Good? Everybody on board with that part? Great. So then, step 4, we'll compare our p-value, 0.1321 to alpha, 0.10. I'll make it have the same number of decimal places. And it's bigger than alpha.
So we failed to reject?
So yeah, we failed to reject. So do not reject H naught. Which means in step 5, blank evidence to blank claim. What was my claim? That 17% are obese. Okay, so first step, since I do not reject H naught, I do not have enough evidence. Everybody good with that part? Alright, there's a not here. If I do not reject, I do not have enough evidence. Yeah.
Why did you write down the z-score in like the third part?
Because when I find my test statistic, when I do one prop z-test, I find my test statistic and my p-value. I should have both of them in there. We can kind of see, is this an unusual z-score? 1.5? Not really. Like right around 2 is where it gets unusual, right? So it should be closer to 2 to be unusual. So that's just another way of measuring it. It's good to have that. Yeah. Good question. Not enough evidence to, and then the second part is my claim, to what the claim. So that comes from step 1. I'll use a different color, orange. That is what goes down there. To reject the claim that 17% are obese. Good. Now, that is not the same thing as enough evidence to support the claim. It could be true, it might not be true. We don't have enough evidence to say either way. Is everybody on board with that? Not enough evidence is weak. It means might be, might not be. And honestly, with a z-score of 1.5, that seems like it might not be true. I just need to I need more evidence. I need to take a bigger sample. Because it's not around 0. It's getting out there. So possibly if I had more evidence, if I took a larger sample, I might be able to prove it. I would just need to have better evidence. Okay, so do people want to check in with your neighbors on this one? Everyone feeling pretty good? Okay. All right, we will move on then. How to use a TI 8384? You do stat test. We're going to, first of all, if you ignore the ones that start with a 2, because those are for 2 samples, these are the options. Which ones are for tests?
All the ones that say test.
All the ones that say test. Which ones are for confidence intervals?
All the ones that's in.
Yeah, all the ones that are in an interval or int. Good? Now, these z-tests, we never use those, ever. Because those are when we have a mean and we know the standard deviation, sigma, which we never know sigma. So those are the ones that are unrealistic. They never occur in real life. So don't ever use those. Instead, for the means, we're going to use t-test for the means. For a proportion test, we use one prop z-test. For an interval, if it's a mean confidence interval, we use t-interval. And for a proportion confidence interval, we use one prop z-interval. It's fairly one-to-one. It makes sense. It kind of lines up pretty well. How would you use them? So for proportions, obviously you get a test. You pick one prop z-test. And then you input all the information here, which this kind of makes sense. And then you end up getting this as your answer. I feel like you guys are all pretty familiar with that at this point. Just as a quick comment, the test statistic is your z-score. And the p-value is this this thing that just is called P, just to give you all a heads up on that one. All right. Now on exams, I will absolutely expect you to give me these things. Same with H0 and H1R. Write down your alpha, find your test stat and p-value using the calculator functions. And then step 4 is all about H0. You're going to reject H0 or fail to reject H0. And then step 5 is summarizing results for your claim. So that kind of involves your claim. So those are all the pieces. I think now it is the one that has in the back. No, it's the one that starts with hypothesis testing, Math 100C group work, Chapter 8 hypothesis testing, friend or foe. Let's get a reader. Okay, go ahead. Great.
Introduction to significant p-value. Do children less than a year old recognize the difference between nice, friendly behavior as opposed to mean, unhelpful behavior? Do they make choices based on such behavior? In a study reported in the November 2007 issue of Nature, researchers investigated whether infants take into account an individual's actions towards others in evaluating that individual as appealing or aversive. In one component of the study, 10-month-old infants were shown a climber character, a piece of wood with googly eyes glued onto it that could not make it up a hill in 2 tries. Then they were alternately shown 2 scenarios for the climber's next try, one where the climber was pushed to the top of the hill by another helper, and one where the climber was pushed back down the hill by another character hinderer. The infant was alternately shown these 2 scenarios several times. Then the child was presented with both pieces of wood, the helper and the hinderer characters, and asked to pick one to play with.
Great. So, right. So in summary, right, there's these 10-month-old babies. They're shown these little scenarios of like this character trying to get up a hill, and then there's one character that tries to help him up, and another character who tries to push him down. Then they're presented with those 2 characters later, the helper and the hinderer, and they're asked to pick one. They alternate which character is the helper and which one's the hinderer, and they also alternate which position they show them to. So I'll show you what I'm talking about in a minute. Unfortunately, the sound is not working, but we'll work with it with closed caption. So here's the little googly eye guy, right? And he tries to go up a hill. So the baby's looking at this, and he's having trouble. And then they end the curtain. And then now they bring in this helper guy who helps him get up to the top, and he's all happy. Right? And then, he's not successful, keeps trying. And then they get this hinderer guy who pushes him down the hill, and then, he rolls off and he's not successful. So they see this several times, and then they're presented with, and I guess they do it over and over to their board by it. And then they have the moms close their eyes, and then the experimenter who doesn't know which one was which brings over the 2 options, and the baby picks one. Now they alternate which one's on the left and which one's on the right, and they also alternate which one is the helper and which one's the hinderer. I mean, from baby to baby. So one baby they'll be consistent, and then the next baby they might swap them. So that's the study. Good? Is everyone kind of on board with this part? So what we're going to do is I'm going to ask you folks to look at some questions. So first of all, identifying the observational units. As a reminder, observational units are the units you're observing. So in other words, if I wanted to know the speed of mice going through a maze, the mice in my sample would be my observational units. Good? And then find the variable. The variable is what you want to know about your observational units, what you're recording, what question you're asking yourself about the observational units. And is that variable categorical or quantitative? And then see if you can answer B and C as well. Right? So counterbalance, incidentally, counterbalance means that they're swapped. So they had some situations where it was one way, and then the next baby they'd swap them and have them be a different way. Good. All right, so I'll give you folks a few minutes with your neighbors to try to answer these questions. All right, so what were my observational units? Who do we observe?
The babies.
Yeah, the 16 babies. And what was the variable? What did I ask myself about each of them?
Who they chose.
Yeah, exactly. Whether they chose, who they chose. The helper or the hinderer. And is that, someone else tell me, is that variable categorical or quantitative? Categorical? Yep. It's not a number, it's a helper hinderer. Yep. Good. Now, the methodology section states for 10 months old, the climber was a yellow triangle, helper hinderer were a red square, blue circle, counterbalanced. Counterbalance again means that they're swapped, right? Sometimes one will be the helper and sometimes the other one, sometimes the red square will be the helper, sometimes the red square will be the hinderer. Also counterbalanced were what position they're presented to. Was it, which one was on the left? Was the helper was on the left sometimes, and with other babies the helper was on the right. Why is it important to do this counterbalance where you mix it up a little bit? Yeah.
I said that it eliminates any effects of consistency.
Right? To be more consistent. Anyone else want to add anything? Yep.
It takes out confounding variables, or at least it tries to.
Right. Tries to reduce those compounding variables because maybe they prefer yellow, or maybe they prefer squares. You know what I mean? So so basically it eliminates the preference for shape or color or left or right. Does that make sense? Left side or right. Maybe they always like the left side or whatever. So it kind of helps all those things. Now, researchers found that 14 out of 16 of them liked the nice toy. What are two possible reasons why they like 14 out of 16 prefer the nice toy? What's one possible reason? Yep.
They like probably the one helping because that's just viewed as something nice.
Yeah, they have a preference for the nice toy, for the nice one. What's another possible explanation? It could be they like the nice toy, or
They like the color blue.
well, they mixed up the colors, so it shouldn't affect it. But
They dislike the mean toy.
no. So either they like the nice toy, or maybe it's just random. Does that make sense for folks? It could just be random. So those are the two possibilities. Either one. Either number one, there is a true preference for nice toy, or it could just be a random chance. Does that make sense for folks? Or people? Okay, good. Okay. If they truly have no preference, if there is absolutely no preference for nicer versus the mean one, out of 16 infants, how many would you expect to choose the nice toy?
8.
8. Yep. Good. Would you always expect it to be exactly 8?
No.
No. It'll vary a little bit. Is everyone on board? So for you, how many out of 16 would you feel it would need to be in order to feel like I really feel like there's a preference. Like 9 probably isn't enough. But how many, if this many out of 16 like the nice toy, how much would it take for you personally to feel like there's a preference here? What do you think?
15.
15 out of 16?
I'd say 12.
12 out of
I'd
16?
say 13.
13? Alright, so 12, 13, 15. Some people need a lot of proof. 12, 13, 15. Okay, sounds good. So just suppose that there really is no preference. Is it possible? Is it possible to get 14 out of 16?
Yes.
Yeah, it's possible, right? Now we're going to take a look and see how likely that is. All right, so we're going to use the one proportion applet. We've seen this before. And we're going to consider possibilities. So let me go over there. So this is my Rossman Chance applet. You can Google it yourself if you want to, but I'll go and do it now. What's the probability of, if there's no preference, you said 50%? How many tosses, how many babies do we have?
16.
16. Great, so let's go ahead and see. Here I got 11 babies saying that they liked the nice toy. I mean, randomly, right? Here are 9. Here 8. 10. And you see how it's coming in here, down here on the bullet below? Another one for 8. Okay. I'm going to do 1,000 of them total. So I have 5 already. I'm going to do 995 more. And there's my nice little thing here. Now I want to know, how many did we have? We had 14 out of 16. So I'm going to see how many are 14 or more. 2 out of 1,000. Okay, so I'm going to reset. And I'm going to do 1,000 again. Start them all over again. And count. This time I got 4 out of 1,000. That seems really high. I'm going to clear it again. Draw samples again. Oops. Reset. My bad. Draw samples again. Out of 14. 3 out of 1,000. Okay. Clear counts. Draw samples. Uh-oh. Reset. Draw samples. This is much different than last class. So I had 1 out of 1,000, 2 out of 1,000, 4 out of 1,000, 3 out of 1,000. Last class I had 1 out of 1,000 like almost all the time.
That's kind of scary for
Yeah.
how consistent that is.
So I would say maybe 2 out of 1,000. I think this might be sort of. So first of all, would you say that it's surprising that 14 out of 16 picked it just by chance? Oh, let's take a look. Let's take a look at this. Actually, while we're at it, what were our other numbers? Someone said that they needed 12 or 13. Let's see how many had 12. Yeah, so that's right around 3%. Does that everyone kind of follow? So that's kind of a typical alpha sort of number, right? 3 is kind of pretty 3% is pretty standard. 13 would be like 1%. That's also pretty typical. 15 might be really hard. There might not be any. Yeah, there's none. So yeah, but like 13 is like 1% chance. 12 is like 3% chance. So that's interesting. All right, cool. All right. So how many of our repetitions had 14 or more? We had about 0.002. Sometimes it was 3 or 4 or 1, but I think the most common number, well, kind of the median number was 2 out of the 5 times I did it. Is everyone good with that part? So that's what we call an approximate p-value. That's roughly the percentage of time we would expect to have that many, 14 or more heads. So remember, a p-value is sort of the probability of getting a sample like yours. We got it 2 times out of 1,000 times. And is that likely or not likely? That's super unlikely. It only happened 2 times out of 1,000. So the smaller the p-value, the less, the kind of less likely that it is to occur. So that kind of casts doubt upon the null hypothesis and says that, remember, the null hypothesis says there's no preference. So it seems like, so here, again, remember, small p-value means that the null hypothesis is probably wrong. Everybody, is this making kind of more sense for folks or not? Everyone, should I say it again? Okay, so so in light of this, would you say that the experimental data observed by researchers provides strong evidence that they have a general preference for the friend over the foe toy, or not very strong evidence? So what do you think? I'll give you folks 15 seconds, 30 seconds to check in with your neighbors. Talk about what you think, Jay, is this, did we end up getting strong evidence that there's a preference, or not very strong evidence that there's a preference? What was the result of 14 out of 16? Is that strong evidence or not?
Strong.
So what did you folks find?
Strong evidence.
Yeah, it's very strong evidence, right? I mean, that's super strong. Why? Because it's really unlikely to get 14 out of 16. All right, so my p-value is 0.002. It's very small. So in other words, super unlikely to get this result randomly. This is the probability of getting it, assuming the null hypothesis is true. So since it's really unlikely, the null hypothesis is probably not true. There probably really is a genuine difference. All right, good. So we're going to just pass these around. All right, so now is a good time to bust out your colored markers or pens if you have any.
This is so bright.
This is the magic formula sheet. Is there enough to pass around all the way around? No? You got people on the other side too, if people can. All right, here is the magic formula sheet. So, actually, I'll start off with the basic one. You'll notice that there's a line down the center, right here. What's up with the left side versus the right side?
Hypothesis versus estimate.
Yep. As long as you see the title, estimate, confidence interval on the left side, hypothesis test on the right side. Then there's also a line through the middle. There should be a line through the middle. So make one, since there isn't one. There's supposed to be a line through the center.
Between the portions and the means.
Say that again, Rafi.
Are you talking about
Yeah,
how it
let's-
divides?
the top and the bottom.
Yeah, the proportions and the means.
Yep, so the means are on top, portions are on the bottom. Everybody good with that?
Yes.
So that splits it into 4 quadrants. If I have a mean, that's the top half, and a hypothesis test, that's the right side, this is gonna be where I find that information. If I had a proportion, that was a confidence interval. Proportion would be the bottom half, confidence interval would be the left half. I'd find the information in here. So, again, these are where the confidence intervals are, and an estimate is the same thing as a synonym for confidence interval. Estimate and confidence interval are the same thing. Just the same as mean and average are the same thing. I mean the same thing. Hypothesis test, and then again means and proportions. So some of these things are kind of critical, like how do you find the critical values? Just look them up in the t-table. For proportions, you'll use the last row of the t-table. For confidence intervals, most of these you may not use the formulas because you folks might just use the calculator functions. But you will need this formula here, the min sample size. The other min sample size for means, we don't really use that one. I'm not going to ask you for that one. But I will ask you for the proportion, so you're going to want that one. And then for hypothesis tests, these are helpful, the H naughts. So mu equals mu naught, P equals P naught. For two proportions or T means, as we'll see later, it's P1 equals P2 or mu1 equals mu2. And then how do you find the test statistic? These are the formulas which you may not use, but you will need the calculator functions. So it does tell you the calculator functions which you can use to find the p-value and the test statistic. There's a couple other things that are useful here. One is the degrees of freedom, which you may end up needing for your homeworks. So cross out the big, giant, complicated formula. It's going to be the smaller n minus 1, because you can have two n's, whichever one's smaller, minus 1. You also might want to circle all of the tests. And then also, this is also super useful. If x is not given, use x equals np and round to the whole number. So those are the things that I would circle here. Everything in red that I have circled is what I would circle here. I'm a little bit concerned. This was super, super useful a year ago when I was making students do, or 2 years ago, when we weren't relying so much on the calculator functions and we were doing the critical value version of the test the traditional way, because I made you all calculate these by hand. But since we're just using the calculator functions now, it may not be as useful. So let me know if you folks end up using it much, and I'll kind of have to make a decision whether I continue with it in the fall, because it may just be that it's sort of obsolete at this point. I'm honestly not quite certain. So we'll talk about that later as we go. All right. But you can use this on exams, so that does make it sort of magic. So this is one of the things you're allowed to have.